All right, folks, let's see where our acceleration equations come from. If we think about acceleration as a definition, it's just a change in velocity over time. And you can see it as a change in speed over time as well. So either one of those kind of work for us. So I could write down that acceleration is a final speed minus initial speed. That's our change divided by the time frame that happened over. Now, it's not a very special equation, but it is going to be useful when we want to derive the other equations, the other three. Now, oddly enough, I'm going to use a speed equation, a constant speed equation, v equals delta d divided by delta t, which doesn't seem to have a place when you talk about acceleration. But when you do a rearrangement here, you get distance is speed times time. So I just rearranged for distance in the situation. And I asked the question, is this v, this speed here, is that instantaneous or is that going to be average? And the answer is it could be either one. Now, if I was to work with an average speed, that gives you a sense that there's a potential that it could be changing. There could be an increase in speed or a decrease in speed. And if you see a change in speed, you obviously have acceleration. So if I wrote that as average, V-A-V-E, this equation is still valid. And I have to think of what an average actually is. Now, when you say an average, I'm thinking of a mean. So when you talk about that, it's just your values add up divided by how many you actually have. If we're only talking about an initial and final speed, we only have two. So I could actually state that the average speed, VAV, the average, is going to be the initial that I have plus the final divided by 2 for the two that I actually have. I could use that and do a quick substitution and say, well, look, I've got this average speed times time. But if I was to take initial plus final divided by 2 that I've defined over here and substitute that in place for VAV in this equation, and now I have something new. Distance is now going to be not average speed times time, but initial plus final divided by 2. VI plus VF divided by 2 multiplied by delta t. And that gives us our second equation. So now we have 1, and we have our second equation. Our third equation, there's a couple ways of looking at it, I suppose, but one of the ones that's easiest to visualize is to look at it in a velocity time graph or a speed time graph. So I'm going to give us a quick y and x axis. I'm going to have speed on the y and time on the x. And I'll give us a scenario where an object's going to start, and it's going to go like this. So what we're seeing is something that's starting off at some defined initial speed and finishing off at some final speed over a time period on the x-axis. Now, we've seen previously that you can actually find out what the distance covered is by looking at the area. So if I was to drop a perpendicular from this point at the end of the graph down to the bottom where you find time, I could divide this into two regular shapes, a rectangle and a triangle. And if I think about it for a moment, I want to find area. That's just for a rectangle, base times height. Base here being time and the height being my initial speed. So I could say that the area is initial speed times time. Now, as you see before, if I'm talking about speed times time, I am talking about distance. So really what I'm calculating here is distance. But that's not enough, though, because that's not what the problem is about. It's not just traveling at some constant speed. It's starting off at this value of VI and finishing at this at VF. So I have to include this area as well. So I'll call this area 1, and this will be area 2. And the difference we see with area 2 is that it's going to be a triangle. And, area of a triangle, 1/2 base times height. I'm working it that way. So my base situation is still the same time frame that I saw here for area 1, but the height is not going to be VI. In fact, the height is going to be something else. It's your VF sitting up top here minus your VI. And that is going to be the actual value. So this height I see here, VF minus VI. So if I want to find the area in this situation, I would say 1/2 VF minus VI times delta t. A little crowded in here, so I'm going to write down what the total area is. So the distance that an object travels in this graph is defined by these two shapes. So total distance, which is your total area. So I could say distance is a total area, which is area 1 plus area 2. So I could say that distance is going to be area 1, which is VI delta t plus my area 2, 1/2 VF minus VI times delta t. So I'll write that 1/2 VF minus VI times delta t. I'm not done yet, though. I'm going to go back to the original acceleration equation I was telling you before, and I said this might actually prove to be kind of useful. So I'm going to restate it over here as acceleration is Vf minus Vi divided by delta t. I'm going to rearrange it now, this time for Vf minus Vi. Vf minus Vi is a times delta t, okay? Not useful by itself, but if I see that I have a commonality here, something that's going to connect them, Vf minus Vi in this equation, and also Vf minus Vi in this equation, they're talking about the same thing, so I can do it again, another substitution, A times delta t. I'm going to take that and substitute it in here for my Vf minus Vi. So now what I end up having is delta d is still going to be Vi delta t plus 1/2, not times the Vf minus Vi I had before, but now what I've substituted in for it, A delta t. So I'm going to have A delta t times again delta t, and you all know that anything multiplied by itself is that value squared. So I'm going to finish off as delta d equals Vi delta t plus 1/2 A and then delta t squared. There's our third acceleration equation. And number 3. Now for our final one, I'm going to go back up here. I have some space, and I want to use this equation I had before. Delta d is Vi plus Vf divided by 2 times delta t. So what I'm going to do is see where else I've seen the time, which has come up here in our first equation. I'm going to combine these to give us our final equation. So I'm going to take equation number 1 and work with equation number 2. So equation number 1, I'm now going to state as delta t equals Vf minus Vi divided by A. So I just rearranged the equation I see over here on the left. I brought the delta t up to the left-hand side by multiplication. I brought the A back down by division. So there's my equation. Delta t equals Vf minus Vi divided by A. I'm doing this because I look at my second equation that we derived. It was Vi plus Vf divided by 2 times delta t. I'm saying here, oh, delta t, by the way, is Vf minus Vi divided by A. So if I was to take that now, and I'm going to insert it into this equation for delta t. So my fourth and final equation we're going to work with this year is going to be delta d equals Vi plus Vf divided by 2 times not delta t, but Vf minus Vi divided by A. Now, this will be a nice little connection to your math classes where you start talking about binomial expansion, because that's what we're seeing in this problem. You're multiplying two effectively fractions, Vi plus Vf, Vf minus Vi divided by A. So those things are going to multiply numerator by numerator, denominator by denominator. So delta d is going to be Vi plus Vf times Vf minus Vi divided by 2A. Kind of a gross equation. It's going to get worse here for a little bit, and we're going to tidy it up and have our final equation. So we think of the different acronyms you might be using to expand on a binomial, FOIL, whatever things you have learned in your math classes, they apply here. So first times first, and then outside times outside, in times inside, then last times last. So that would run us into delta D is Vi Vf. So I'm going to say Vi Vf, our outside Vi times negative Vi. So I get minus Vi squared. The inside Vf plus Vf squared. And our last positive Vf, negative Vi. So minus Vf Vi. And again, divided by 2A. Gross looking equation. But I notice I actually have two values that are the same. Vi times Vf, Vf times Vi. One is positive, one is negative. They're going to cancel out. So that's gone, and now that's gone. So I run into is delta D is negative Vi squared plus Vf squared over 2A. We're not a huge fan of having a negative start off a problem or to start off an equation, so I could rearrange it into a form we're more familiar with, which is delta D is Vf squared minus Vi squared all over 2A. And that is our fourth and final equation that we can use to solve pretty much any kinematics equation. So although these are the four we're going to work with this year, we're going to have to do some similar problems, some similar ideas where we do some substitution to give us some other equations to solve more complex kinematics problems. But nonetheless, there they are for us.